What you are seeing isn't real. In 2011, New York University scientists discovered something shocking: objects that threaten us seem closer than they really are. Our brain bends reality, making danger feel nearer to protect us, hijacking our perception instantly. 11 years later, University of California researchers uncovered something even stranger. Our brain needs about 15 seconds to piece together all the visual info into one image. That means you're always living a little behind, trapped in a blurry past stretched out by fractions of a second. Imagine a bird flying past your window. The instant you see it, that event already happened seconds ago. Your mind is a constant slow-motion replay buffering reality, always lagging. This delay between now and what you perceive is a hidden fact of life. Here's a mind-blowing twist. Our sun, famous for its yellow-orange glow, is actually green. It emits more green photons than any other color, but our atmosphere absorbs and mixes light, scattering blue and shifting the sun's color to familiar yellows and reds. What we see is just a tiny slice of all electromagnetic waves emitted not only by the sun, but everything around us. Ultraviolet rays give you a tan, infrared warms your skin, you rebathing in waves invisible to your eyes, a constant tidal ocean of radiation. The sun produces something else, almost unbelievable, something so elusive. We didn't even know it existed until the mid-1900s. This something is billions of times more abundant than visible matter itself. It's so ghost-like that early physicists thought it couldn't ever be detected. These ghost particles can pass through a lead wall 1 light-year thick 10 trillion kilometers without any collision. Right now, 100 trillion of these particles pass through your body every second, unseen, unstoppable, moving endlessly through the universe's void like phantoms. Called neutrinos, these particles hold answers to why the universe exists, why matter exists over emptiness, how stars explode, and what happened in the first second after the Big Bang. Unlike light, neutrinos escape the hot, dense early universe untouched, carrying pristine cosmic secrets. Right at this moment, about 25 million relic neutrinos from the dawn of time pass through every point in space and through your body. These are echoes of the early cosmos, invisible witnesses to the birth of everything we know and cherish. To understand why neutrinos matter so much, we must dive into their strange history. Their existence was denied by top scientists, and proving them took 3 decades, challenging the very foundations of physics and raising the ultimate question: why is there something rather than nothing? Neutrinos are ghosts in physics, invisible yet real. How can something exist yet leave no trace? How do you chase something that doesn't interact with anything? The quest for neutrinos is a tale that throws light on the very nature of reality itself. It all started in December 1930 with Wolfgang Pauli, a brilliant physicist gone through heartbreak and chaos, battling personal demons and physics conundrums. Pauli penned a desperate letter proposing a wild solution to a baffling problem in nuclear physics. The problem was beta decay, when a neutron turns into a proton and emits an electron. But energy wasn't conserved. Some vanished like magic. Either physics was broken, or something invisible was stealing energy. Pauli chose to believe in the invisible. Pauli proposed a tiny, neutral, almost non-interacting particle escaping unnoticed, a ghost particle carrying away the missing energy. He called it the neutron. He feared it was untestable, a scientific sin, and bet champagne it'd never be detected. In 1933, Enrico Fermi picked up Pauli's idea and turned it into a revolutionary theory detailing a new fundamental force, weak interaction, explaining nuclear decay and the sun's fire. He renamed the ghost particle neutrino, the little neutron in Italian. Fermi's paper was shockingly rejected by Nature for being too speculative. It got published quietly in an Italian journal years later. It was hailed as one of the greatest achievements in physics, shaping our understanding of the universe's fabric. In the Soviet Union, physicist Gamow dreamed of escape and made a cosmic joke, composing the Alpha Beta Gamma paper explaining how neutrinos fuel star births and deaths. Neutrinos became thieves of stars' energy, cooling them rapidly, a cosmic roulette of energy loss. Neutrinos sneak away energy from dying stars almost invisibly. This Urca process was whimsically named after a casino where money vanishes fast. Incredibly, neutrinos are the universe's stealthy energy robbers, invisible yet vital to cosmic life cycles. By 1951, neutrinos was still theories, but fate intervened when physicists Rheanes and Cowan met during a plane's emergency landing. They sketched the impossible, set up detectors near reactors to catch neutrinos escaping atomic chaos, exorcising ghosts from physics. Placed a massive detector 40 meters underground near a nuclear reactor, designed to detect flashes when neutrinos collide with atoms. A staggering 615 tons of water and hundreds of photomultipliers awaited the invisible visitors, rare signs. When a positron flashes and then a neutron is absorbed by cadmium shortly after, the signature double flash reveals neutrino interaction. a whisper from the universe confirming Pauli's wild ghost particle was real. The neutrino had been caught at last. Pauli, having bet champagne it would never be found, laughed and uncorked the bottle 26 years later. His idea wasn't tea madness, it was a revolution, proving invisible neutrinos truly exist, rewriting physics and bridging dreams with reality. Fermi's weak interaction theory eventually became the foundation of particle physics. Recognition took decades. Success comes slow in science. Awards may arrive late, but they honor visions that reshape our understanding forever, embodying perseverance and genius. At the heart of it, the sun is a colossal thermonuclear furnace. Every fusion event turns protons into neutrons, emitting quadrillions of neutrinos every second, relentlessly piercing your thumbnail with invisible messengers, forever linking us to the sun's core. Davis imagined catching these elusive neutrinos, unlike photons, which take thousands of years battling atoms inside the sun before reaching us. Neutrinos fly directly out. They offer a real-time snapshot of the sun's heart, an impossible yet tantalizing. Davis built a giant tank filled with 615 tons of perchloroethylene, a chemical cleaner primed to trap neutrinos. The task was like searching for a single grain of sand on a kilometer-long beach, requiring extreme patience and innovative techniques. Davis's genius was adding helium bubbles to the liquid, turning invisible neutrino interactions into detectable flashes. Battling background radiation and noise from nearby towns, he fought on, determined for the hardest science solve humanity had ever attempted. In 1967, Davis compared his results with theoretical predictions. Only a third of the expected solar neutrinos were detected. It was a physics disaster. The missing neutrinos either never existed or were hiding. A cosmic puzzle ignited debates and disbelief. For 3 decades, Davis refined his experiments, enduring skepticism and accusations of error. Every time, the neutrino shortfall stayed. The sun was either misunderstood or neutrinos were behaving in ways science couldn't explain yet. Meanwhile, Masatoshi Kashiba fought his own battles: childhood illness, teachers who doubted him, and experimental failures. Yet he persevered, leading a team to build a massive detector first designed for proton decay, later repurposed to hunt neutrinos. When particles travel faster than light through water, they create Cherenkov radiation, distinctive blue glow shaped like a cone. Kashiba's detector used this effect to trace neutrinos, reconstructing their direction and energy with stunning precision underground. February 23, 1987, a massive star exploded in a supernova. Before light even reached Earth, neutrinos flooded detectors worldwide. Kamiokande in Japan, Baksan in Russia, and others, all registering 24 neutrinos from that cosmic blast. The detectors caught only 24 neutrinos out of quadrillions passing. It was enough to prove that most of the supernova's energy happens in the invisible neutrino realm. This discovery birthed neutrino astronomy, a window into the universe's hidden drama. Despite breakthroughs, the solar neutrino problem persisted. Davis kept detecting only a third of expected neutrinos. Science was at a crossroads. Was the sun different than predicted, or were neutrinos changing their nature unbeknownst to us? The Sudbury Neutrino Observatory in Canada, buried deep underground with 1,000 tons of heavy water, promised answers. It was more sensitive and could detect neutrino types earlier detectors missed, ready to solve decades-long mysteries with cutting-edge precision. Breakthrough neutrinos switch flavors, while traveling electron muon, tau, meaning many escaped Davis's detectors simply by changing type. The missing neutrinos were never lost. They were invisible to earlier instruments, a cosmic shape-shift of ghost particles. For over 30 years, Davis's work was doubted, but with the Sudbury results, he was proven right. The skeptic turned hero. In 2002, Davis and Kashiba were awarded the Nobel Prize, a triumph of persistence, faith in data, and the hidden dance of neutrinos. Neutrinos, once doubted ghosts, now illuminate the universe's deepest secrets, from star explosions to the Big Bang. Their story reminds us that the unseen can hold the keys to everything, inviting us to look beyond surface fear and mystery. What the reality we see is just a slice. Neutrinos challenge our senses, pushing us to embrace the unknown. They whisper that existence is complex. To understand the cosmos, we must chase shadows and trust the unseen. Ultimately, neutrinos urge the greatest question: why is there something rather than nothing? These ghostly travelers tell a story not just of particles, but of existence itself, inviting us to ponder the cosmic mystery at the heart of all things. Objects appear closer when they pose a threat because our brains bend reality to protect us. Fear warps time and space, making danger loom larger and nearer than it actually is. Brain takes about 15 seconds to combine visual information into a clear image. This creates a time lag. You live a few seconds in the past, a hidden delay in every moment of your life. Contrary to what we see, The sun actually emits more green light than any other color. Our atmosphere modifies this light, scattering blue and making the sun appear yellow, orange, or red instead. Our waves beyond visible light flowing through space. UV rays tanning us, infrared warming us. We constantly bathe in radiation we can see, a hidden ocean of light beyond human sight. Among this sea of radiation, there are ghostly particles from the sun that pass through everything, Earth, your body, lead walls, without stopping or interacting, ghost-like and mysterious. Neutrinos flow through us and the cosmos, remnants of the Big Bang, carriers of cosmic history and answers to fundamental questions about existence, matter, and cosmic evolution. The story of neutrinos is full of denial, discovery, and drama, from a scientist's desperate letter to decades of search and finally recognition. Their tale reveals the twists and turns of scientific progress. Wolfgang Pauli was torn between turmoil in his personal life and challenges in physics. He faced the beta decay mystery where energy vanished, and in despair, dared to propose an invisible particle to save physics. Pauli suggested a neutral, nearly undetectable particle fleeing the nucleus, carrying away missing energy. He called it a neutron, though later renamed neutrino, admitting he feared this might never be proven. Enrico Fermi developed Pauli's idea into a comprehensive theory of beta decay, introducing a weak force of nature and naming the particle neutrino. His work connected mysterious decay with new physics fundamentals. Fermi's paper was rejected by the biggest scientific journal for being too speculative, yet this supposedly wild theory laid the groundwork for modern particle physics, enduring quietly until its truth was undeniable. Gamow, escaping Soviet difficulties, helped reveal neutrinos' cosmic role, jokingly naming a paper Alpha Beta Gamma after the authors. He unveiled neutrinos as star energy thieves, quietly stealing heat and cooling the universe's furnaces. Neutrinos slip out of stars, carrying away energy faster than any other process. This escape mechanism was nicknamed Urka, a casino where money disappears quickly, perfect for describing neutrinos' stealthy energy theft. In 1951, physicists Riones and Cowan conceived an experiment to catch neutrinos, from a plane emergency landing to designing underground detectors. Their journey was a fight to trap ghosts passing through walls. The plan involved placing a detector near a nuclear reactor to detect rare neutrino collisions. Massive water tanks and photomultipliers formed a shielded trap, awaiting the invisible particles' faint, elusive signals. They identified neutrinos by capturing a positron flash followed shortly by a neutron absorption flash. This twin flash was the unmistakable signature proving neutrinos exist, a bullet finally catching a ghost after decades of chase. Pauli admitted he was wrong about neutrino invisibility, popping the champagne 26 years after his bet. His invisible particle was real, a triumph of perseverance, imagination, and courage to challenge accepted physics. Fermi's theory reshaped physics but initially went unnoticed. Science demands patience. Discoveries often take decades to be embraced. The story reminds us greatness often comes quietly, long before the world notices. Within the sun's core, nuclear fusion turns protons to neutrons, releasing quadrillions of neutrinos every second. These tiny messengers pierce everything, connecting us invisibly to the heart of our star. Ray Davis built an enormous detector filled with cleaning fluid to trap solar neutrinos. His bold goal, to see inside the sun in real time, catching ghost particles that travel straight through the solar furnace to reach Earth. Davis's 615-ton tank of perchloroethylene was a needle in a haystack project, seeking a whisper of interaction among countless invisible neutrinos. His experiment was a battle of patience, physics, and sheer will. Bubbling helium inside the tank, Davis turned ghostly neutrino hits into flashes of light against relentless background noise. He chased these flickers, determined to prove neutrinos were no longer just theory. Davis's measurements showed only 1/3 the expected neutrinos from the sun were detected. The missing 2/3 vanished without explanation, a crisis shaking the foundations of solar physics and particle science. For 30 years, Davis refined his experiments, facing skepticism but confirming the neutrino shortfall every time. The sun's output or neutrino behavior, one or the other had to change established physics rules. Satoshi Kashiba, once discouraged by teachers and health battles, led the creation of a giant particle detector in Japan. What started as a quest for proton decay slowly turned into groundbreaking neutrino observations. Kashiba's detector could track neutrinos by detecting Cherenkov radiation, a unique blue glow produced when particles move faster than light in water, revealing direction and energy of these ghostly travelers. In 1987, neutrinos from a distant star's supernova explosion reached Earth hours before visible light, proving these particles are key messengers of cosmic cataclysms, illuminating events shrouded from telescopes. Capturing just 24 neutrinos from that blast, scientists launched a new branch of astronomy focusing on neutrinos, opening a window into the universe's invisible forces and hidden phenomena beyond light's reach. Sudbury Neutrino Observatory, buried deep in a Canadian mine, used heavy water to finally solve the solar neutrino mystery. It detected all neutrino flavors, proving neutrinos transform and evade earlier detectors. Neutrinos switch between electron, muon, and tau flavors as they travel. This remarkable shape shifting means detectors sensitive only to one kind miss many neutrinos, explaining years of missing particles and opening new physics frontiers. After decades of doubt, Davis's painstaking work stood tall. His results were sound, revealing neutrinos' true nature. In 2002, the Nobel Prize honored both Davis and Kashiba for unveiling the neutrino's cosmic secrets at last. A theoretical ghost to a key cosmic courier, neutrinos reshape our understanding of cosmology, stars, and fundamental physics, proving that invisible forces govern the universe's greatest mysteries. Neutrinos push us to look beyond what we see, reminding us the universe is complex, full of hidden layers. To truly grasp existence, we must chase the invisible and embrace uncertainty. Ultimately, neutrinos invite us to ponder the biggest question of all: why is there something rather than nothing? A question scientists, philosophers, and dreamers continue to explore, inspired by these ghostly particles. Fear tricks our brains, making danger seem closer and more urgent than it really is. This survival tweak distorts reality, making the world a more threatening place, and keeping us alert and alive. While our perception is delayed, our brains spend precious seconds piecing together sensory input before presenting us a clear picture, meaning we never directly experience the present, only a carefully constructed recent past. Despite its yellow glow, the sun emits most strongly in green light. The atmosphere's layers filter and scatter sunlight, coloring what we see, masking the sun's true vibrant nature behind a warm mask. Beyond visible light, our world is swamped by waves we can see: ultraviolet, infrared, radio waves. These invisible waves flow through us constantly, an ocean of radiation underpinning our everyday reality. Our star also showers us with elusive particles called neutrinos, ghost-like and intangible. They travel unimpeded through matter, billions passing through our bodies every second without us ever noticing. Neutrinos come from the universe's earliest moments, carrying information unreachable by light. They are silent witnesses to the Big Bang and celestial events, unlocking secrets of existence and cosmic evolution. Despite their significance, neutrinos were initially denied by top physicists. The scientific journey to prove their existence was long and brutal, a tale of skepticism, resilience, and eventual triumph. Faced with an energy crisis in physics, Wolfgang Pauli suggested a hidden particle stealing energy unseen. Despite fearing ridicule, he dared propose the neutrino, a phantom that would alter physics forever. Pauli called the particle a neutron, later renamed neutrino by Fermi. The diminutive name reflected the particle's ghostly subtlety and key role in unraveling fundamental physical laws. Fermi crafted a theory explaining beta decay through weak interaction, introducing neutrinos as critical actors. His ideas connected particles and forces, redefining modern physics landscape. Though initially rejected by the leading journal, Fermi's paper laid foundational concepts that transformed particle physics, proving sometimes the loudest ideas start as whispers ignored. Mo's work linked neutrinos to cosmic processes, likening their energy theft to fast money disappearing at a Brazilian casino, illustrating neutrinos' stealthy cosmic role with humor and insight. The Urca process describes how neutrinos cool stars by carrying away energy. This invisible energy drain keeps stars alive longer, underscoring neutrinos' immense but hidden cosmic influence. Inez and Cowan designed an experiment to exorcise the neutrino ghost by catching it near nuclear reactors, hoping to prove its reality after decades of speculation. They built a massive detector underground, filled with water and sensors, aiming to spot the rare flashes caused by neutrinos colliding with atoms, transforming theory into tangible proof. Neutrinos hit, they create a two-stage flash: first a positron glow, then neutron capture light. Spotting this allowed scientists to finally confirm neutrinos exist, defeating years of doubt. Pauli's long-lost champagne bet was popped in celebration. The neck-breaking chase of an invisible particle ended in victory, proving the power of imagination and persistence in science. Recognition for Fermi's work was slow, but history would honor his insights as foundational. The journey reminds us innovation often faces resistance before reshaping knowledge forever. Star burning bright with fusion, emits quadrillions of neutrinos every second, these ghostly messengers penetrate the Earth and every living being, linking us invisibly to the cosmos. Ray Davis took on the challenge to catch solar neutrinos in a massive chemical bath, aiming to see the sun's core in action, though it meant chasing particles nearly impossible to track. His tank of hundreds of tons of cleaning fluid was the stage for a cosmic hunt. Capturing a faint interaction among an ocean of invisible neutrinos was like finding a single whisper in a hurricane. By injecting helium bubbles, Davis made invisible hits flash like tiny beacons inside the liquid, transforming his massive tank into a neutrino hunter's dream and nightmare all at once. The result shocked science. Only 1/3 of neutrinos predicted by solar models were detected, where had the rest vanished. The missing neutrino mystery challenged physics for decades, shaking trust in models and data. Undeterred, Davis repeated his experiments for 30 years. Every attempt confirmed the same anomaly. The missing neutrinos taunted scientists, opening new questions about the sun, matter, and fundamental forces. Sheba battled illness and doubt to lead a giant detector-s construction, shifting focus from unmet goals to the neutrino hunt, turning setbacks into a new gateway for discovery. His detector used Cherenkov radiation, the telltale blue light from particles moving faster than light in water, to track neutrinos, unveiling their path and energy in an otherwise dark invisible. In 1987, a star exploded, sending neutrinos blazing through space hours before light. Detectors worldwide caught 24 neutrinos, a faint but profound cosmic message from a dying star's heart. That moment birthed neutrino astronomy, studying the universe through these ghostly messengers, revealing cosmic events invisible to all other means of observation. Sudbury Neutrino Observatory's sensitive instruments finally solved the solar neutrino puzzle, revealing neutrino flavor switching and reshaping understanding of particle physics and the sun's inner workings. Neutrinos switch among electron, muon, and tau flavors during travel. This shifting fooled early detectors, which could only see one kind, explaining the decades-old missing neutrino mystery. Ray Davis and Masatoshi Kashiba received the Nobel Prize, honoring their groundbreaking work decades after first detection, a testament to patience and pioneering spirit in uncovering cosmic mysteries. Neutrinos hold keys to cosmic origins, star lives, and fundamental forces, proving that sometimes the universe's biggest secrets lie in the smallest, most elusive places. The universe challenges our senses, offering deeper layers of reality beyond visible light, inviting us to embrace mystery, quest for knowledge, and humility in uncovering truth. Through neutrinos, science nudges us toward the eternal question, why is there something rather than nothing? This ghostly puzzle remains open, inspiring both wonder and relentless curiosity. Fear triggers our brain to manipulate reality, making threats look closer, sharper, and more urgent than they really are, to keep us safe but warp our perception. Brain takes time, about 15 seconds, to form a visual reality from scattered data. We don't live in the exact present, but in a constant slow-motion playback of recent moments. Our sun's true color is green, more than yellow or orange. Atmospheric effects like blue light scattering cloak this reality in warm hues we are familiar with. The world is bathed in invisible waves, ultraviolet, infrared, and beyond, painting a hidden cosmic backdrop to everything we see and feel, invisible yet vital. Among the particles, the sun floods space with neutrinos are rare, ghostly entities passing through everything, including you, carrying secrets of stellar cores invisible to ordinary senses. Born moments after the Big Bang, neutrinos traverse the universe untouched and unchanged, silent storytellers of the cosmos, earliest and most profound moments. Despite their cosmic importance, neutrinos were initially doubted by experts, proving their existence required decades of dogged research against disbelief and skepticism. In 1930, Wolfgang Pauli wrote a letter proposing a new particle to save energy conservation in physics, risking his reputation on a mysterious invisible particle, the beginning of the neutrino saga. Pauli's particle was called the neutron initially. Later, Fermi named it the neutrino, a little neutral one, highlighting its tiny, ghostly presence at the heart of nuclear mysteries. Fermi built a theory linking neutrino emission to radioactive decay, unveiling a new fundamental force and shifting how we understand matter and energy's dance. Though rejected initially for daring to speculate, Fermi's ideas became pillars of modern physics, a testament to the power of bold innovation beyond immediate acceptance. Gamow laughed with colleagues, naming a paper Alpha Beta Gamma to spoof physics, naming traditions while unveiling neutrinos' vital role as energy thieves inside stars. The Urca process describes neutrinos stealing stellar energy, cooling stars like money vanishing at a casino, both clever and cosmic, highlighting neutrinos' odd but crucial role. Rionese and Cowan's labors birthed the first neutrino detector experiments, transforming theory into tested reality, exorcising ghosts and validating decades-old puzzles underground. Their detector, shielded underground and brimming with pure water, awaited the faintest signs of neutrino collisions, a colossal vigil to catch particles that refused to be caught. Detecting a positron flash followed by neutron absorption created a unique double flash signal, the Neutrinos' calling card and proof of its ghostly existence finally revealed. Pauli, once lamenting having postulated an undetectable particle, celebrated its discovery decades later, a triumph for science and belief in the unseen. Though overshadowed early on, Fermi's theory helped redefine particle physics, inspiring generations of scientists unwavering in pursuit of knowledge beyond visible horizons. The sun constantly releases a torrent of neutrinos, billions streaming through every second, linking life on Earth to cosmic processes unreachable by any other means. Ray Davis designed a vast underwater detector to spot neutrinos, fighting the odds to see beyond light and capture the sun's invisible messengers. With 615 tons of fluid, Davis searched for a few fleeting flashes, minuscule signs, amid overwhelming invisibility, testing the limits of patience and precision in science. Bubbling helium through the detector fluid, he transformed neutrinos, silent touch, into visible signals, turning ghosts into light, inching science closer to sun's secrets. The baffling shortfall of neutrinos in Davis's results stirred controversies. Was solar models wrong, or had neutrinos changed in unknown ways? The mystery hung heavy over physics for decades. For 30 years, Davis defended his data amid skepticism, solidifying one of the longest scientific quests, proving faith in results through relentless repetition. Satoshi Kashiba overcame illness and early setbacks, leading a unique neutrino observatory, turning obstacles into opportunities, reshaping neutrino science forever. Kashiba's detector leveraged Cherenkov light, the brilliant blue bloom of fast particles in water, to trace neutrino paths, turning intangible particles into visible phenomena. In 1987, a star's final death sent neutrinos racing through space, reaching us hours before its light, imprinting a telltale cosmic fingerprint on detectors worldwide. This event opened neutrino astronomy, allowing us to hear cosmic explosions invisible to light, unveiling the universe's hidden stories and energetic drama. Sudbury Observatory discovered neutrinos change types en route to Earth, confirming Davis's partial detection was due to these flavor shifts and completing the solar neutrino story. Electron, muon, and tau neutrinos dance a quantum tango, shifting forms during flight and challenging our detection methods, nature's ultimate disguise within fundamental particles. After decades of doubt and silence, Ray Davis's pioneering work was honored with the Nobel Prize, acknowledging the quiet hero who unveiled a cosmic mystery. The elusive neutrino dawns as a key to understanding the universe's origins, stellar life cycles, and fundamental forces, a whisper revealing the cosmos' deepest truths. Learning from neutrinos teaches us that what we see is only a slice of reality, urging humility and exploration beyond sensory limits into unseen cosmic realms. Neutrinos leave us with the timeless question, why is there something instead of nothing? A riddle fueling both science and philosophy, inviting endless questing and wonder. Fear isn't just emotion, it rewires perception, bending reality to make dangers loom nearer and sharper, a primal survival hack twisting how we grasp the world's hazards. Brain takes about 15 seconds to assemble images into a coherent picture, meaning we always perceive the world in a slight delay, a tiny lag in consciousness. Beneath its golden hue, the sun radiates strongest in green light, masked by Earth's atmosphere, which scatters shorter wavelengths, hiding the star's true shade from our eyes. The world is immersed in an ocean of invisible waves from ultraviolet to infrared, carrying energy we never see, shaping life and environment beneath the surface. Amid this wave ocean, neutrinos flow silently, passing through matter and people alike, unnoticed yet integral threads woven into the cosmic fabric. Emerging seconds after the Big Bang, neutrinos preserve cosmic history, traveling unaltered across eons, bearing quiet testimony to the universe's fiery birth. Despite their cosmic prominence, neutrinos were once dismissed by leading scientists, proving their reality was a long, rigorous challenge filled with doubt and resistance from the physics community. Wolfgang Pauli risked scientific scorn by proposing an undetectable particle to uphold energy conservation laws, setting the stage for neutrino research that would span decades. Fermi renamed Pauli's particle neutrino, a small neutral particle, a subtle name matching its elusive nature, central to unraveling mysteries of nuclear decay. Fermi's beta decay theory exposed the weak force responsible for nuclear transformation and particle emission, transforming the physics understanding of matter and interactions. Controversial nature of Fermi's work led to initial rejection, a common fate for paradigm-shifting ideas that challenge the scientific status quo. Combining science and humor, Gamow named a key neutrino paper, Alpha Beta Gamma, a pun reflecting both physics concepts and the authors themselves, infusing levity into serious work. Urca process, named after a casino, describes neutrinos stealing energy, cooling stars rapidly, highlighting their strange yet essential role in astrophysics. Inspired by chance and determination, Riones and Cowan planned underground neutrino detection, combining theory with daring experimental design to hunt the invisible. Their underground detector, loaded with water and sensors, stood ready to capture elusive hits, a fortress against invisibility designed to catch particles that pass through everything. The unique double flash, a quick burst followed by delayed glow, became the unmistakable indicator of neutrino collisions, turning theory into reality with glowing proof. Neutrinos were finally detected. Pauli toasted decades of doubt and discovery, celebrating science's triumph over the invisible and impossible. Despite initial silence, Fermi's work illuminated particle physics, inspiring generations to look deeper into nature's fundamental mysteries. The sun floods Earth with quadrillions of neutrinos every second, linking us invisibly to stellar processes beyond sight and sound. Ray Davis constructed an underwater observatory dedicated to catching neutrinos, shining a light on the sun's hidden fusion heart with pioneering resolve. With colossal patience, Davis searched for rare neutrino interactions in a vast liquid tank, a monumental task akin to catching whispers amid storms. Helium bubbling revealed neutrinos, invisible passes as visible light flashes, turning ghost particles into detectable signals. Davis's findings revealed a shocking gap: only 1/3 of predicted neutrinos detected, igniting a decades-long scientific mystery and debate. For 30 years, Davis defied critics, refining methods and confirming results, embodying relentless scientific perseverance. Childhood illness and discouragement, Kashiba rose to lead cutting-edge neutrino experiments, transforming setbacks into breakthroughs. Kashiba's detector used Cherenkov radiation to trace neutrinos, revealing paths of particles moving faster than light in water, a beacon in the dark. In 1987, neutrinos from a distant star's violent death burst through space, reaching Earth before visible light and signaling cosmic events invisible to the eye. Detection of supernova neutrinos founded a new field, neutrino astronomy, expanding our cosmic senses beyond light to the invisible. Deep beneath Canadian soil, Sudbury Observatory's heavy water revealed neutrino flavor changes, completing the solar neutrino puzzle and expanding physics frontiers. Neutrinos shift flavors among electron, muon, and tau states mid-flight, nature's particle sleight of hand that baffled science for decades. After years of skepticism, Davis's work earned the Nobel Prize, affirming his decades-long quest to measure the sun's invisible neutrino flux. These elusive particles unlock answers about the universe's origin, the life and death of stars, and fundamental forces governing reality. Understanding neutrinos pushes us beyond what our eyes can see, challenging perceptions and inviting us into the universe's hidden depths. Neutrinos lead us to ponder why anything exists at all, a question stretching science and philosophy to their limits, fueling endless exploration. Fear doesn't just alert us, it distorts our sense of time and space, making threats loom unnervingly close and urgent beyond reality's bounds. Mind's 15-second assembly delay means we live slightly behind the actual moment, our reality, a carefully pieced together memory rather than a live show. Though yellow to us, the sun's raw emission peaks in green light, but atmospheric escapes and scattering cloak it, hiding true colors beneath an earthly veil. Waves beyond visible light saturate space unseen, but vital from UV rays to infrared warmth, all shaping the universe and life hidden beyond perception. Among the invisible flow, neutrinos pass undisturbed through matter and us, a silent majority bearing cosmic secrets and energy, unnoticed but everywhere. These particles traveled untouched since the universe's first seconds, frozen messengers of cosmic origins, carrying secrets no other particle can tell. The neutrino's tale is one of initial denial by science giants, followed by decades of experiments turning hypothesis into fact, a saga of dogged determination. Pauli's letter proposed a hidden particle to account for mysterious energy loss in beta decay, presenting a radical challenge to physics norms. Fermi coined neutrino, capturing the particle's small and elusive essence, a linguistic tribute to its subtle yet essential nature. Fermi's beta decay theory exposed weak interaction, a fundamental force behind nuclear processes pivotal for modern physics. Fermi's insights met resistance, delaying their acceptance. Yet today, this work underpins a vast swath of physics understanding. Fermi's playful naming of neutrino research injected humor and humanity into the hard, technical world of physics, lightening profound discoveries. The Urca process shows neutrinos stealing energy from stars as stealthy thieves, a bizarre but vital astrophysical phenomenon. Sudden plane landings sparked a conversation that birthed the first neutrino detector plan, highlighting chance and curiosity in scientific breakthroughs. Their underground setup surrounded a reactor with massive tanks and sensors, ready to catch near impossible neutrino interactions. Detecting two closely timed flashes, the signature neutrino mark turned ghost particles into measured phenomena, a triumph of experimental ingenuity. Pauli's skepticism gave way to celebration after neutrino detection, honoring science's patient chase of the invisible. Fermi's pioneering efforts, once ignored, now shine as keystone of modern particle physics, inspiring generations to pursue the unseen. Our sun bombards Earth with neutrinos in unimaginable numbers every second, invisible links between us and star's core processes. Davis devoted decades building a grand detector underwater, a beacon to catch silent neutrinos revealing solar secrets in real time. Searching among countless neutrinos, Davis sought faint flashes in his massive tank, a monumental gamble amid cosmic silence. Davis's innovation of helium bubbles transformed neutrino hits into flashes of light, allowing science to see the invisible touch of cosmic particles. When Davis found only a fraction of expected neutrinos, the gap sparked a perplexing mystery that puzzled physicists for decades. Through critiques and doubts, Davis persevered, rigorously confirming results and standing firm in the face of scientific uncertainty. From childhood illness to academic challenges, Kashiba's resilience led to a transformative observatory in neutrino science. Using Cherenkov radiation, Kashiba's team illuminated neutrinos' paths, revealing particle journeys through blue light cones beneath the Earth. 1987 witnessed a star's death heralded by neutrinos beating light to Earth, a cosmic signal opening new sights into galactic phenomena. Its burst sparked neutrino astronomy, a new way to witness the universe's hidden events through particles, rather than light alone. The Sudbury Observatory revealed neutrino flavor change, solving the decades-old solar neutrino puzzle and rewriting particle physics textbooks. Neutrinos' journey, they morph among flavors, a quantum trick baffling scientists until the Sudbury discovery. Decades after his groundbreaking detection, Davis received the Nobel Prize, a crowning achievement acknowledging his unwavering quest. Neutrinos open doors to understanding the universe's birth, star cycles, and fundamental forces governing reality. This invisible world challenges humans to expand senses and knowledge, a humbling invitation to explore beyond light and matter. Neutrinos provoke the eternal question of existence why, prompting science and philosophy to seek ever deeper answers. Fear twists our view, making dangers appear nearer and more formidable, a primal trick to keep us alert through distorted perception. Brain's 15-second processing time means we don't see events as they happen but a stitched together, slightly aged picture of reality. Our atmosphere masks the sun's true green glow, presenting a golden mask that hides the star's dominant color from human eyes. Beyond sight, a vast spectrum of electromagnetic waves inundates Earth, carrying energy and information critical to life but unseen. Among these waves, neutrinos broadcast silently, passing unimpeded through matter, making the universe a far stranger place than we imagine. Neutrinos formed moments after creation, journeying unaltered through time and space, cosmic echoes preserving the universe's original secrets. Initially dismissed, neutrinos were the center of decades-long scientific battles, culminating in breakthrough detections and recognition. Pauli took a monumental risk, proposing an invisible particle to uphold physics laws, a gesture of desperate hope and insight. The term neutrino highlighted the particle's smallness and neutrality, embedding its ghostly nature into physics language forever. Fermi's theory revealed weak interaction, reshaping how we understand nuclear decay and particle emission processes. Rejection met Fermi's groundbreaking work first. Later acclaim followed an epic pattern in science's march forward. Amo injected humor into neutrino research through playful naming, mixing science and jest in cosmic settings. Neutrinos help stars cool by stealthily carrying away energy, a dark secret named after a casino where money disappears swiftly. Viennese and Cowan's unexpected airport conversation led to designing the first neutrino detector, igniting a new era of particle physics. Our underground detector employed massive water tanks and sensitive photomultiplier tubes, awaiting faint neutrino signals from nuclear reactors nearby. Twin light flashes, a positron burst followed by neutron absorption, signaled neutrino collisions, proving these ghostly particles' tangible existence. Pauli's speculative ghost particle gained solid footing, turning decades of doubt into a celebrated scientific reality. Though initially ignored, Fermi's vision reshaped physics, laying the foundation for understanding fundamental forces and particles. The sun continuously pumps neutrinos through space and Earth, linking us invisibly with the fiery heart of our star. A. Davis's monumental underground detector stands as a sentinel for neutrinos, detecting whispers of solar processes through ingenious design. Capturing neutrinos is like finding a single grain on a vast beach, requiring monumental patience and precision against enormous odds. Helium bubbles reveal neutrino impacts as flashes of light, turning the invisible into the seen, one small glow at a time. Puzzling deficit of solar neutrinos found by Davis sparked 30 years of intense scientific investigation and debate over the nature of neutrinos and the sun. Undeterred by criticism, Davis persisted over decades, refining his methods and solidifying his findings in the face of skepticism. From adversity and doubt, Kashiba emerged to lead neutrino research that opened new horizons in particle physics and astronomy. Using Cherenkov light, Kashiba's team traced neutrinos, transforming invisible particles into trails of glowing blue light beneath the Earth's surface. In 1987, neutrinos from a collapsing star blazed past Earth before visible light, delivering a new cosmic messenger's message to detectors worldwide. This event launched neutrino astronomy, revolutionizing how we observe the universe's most violent and hidden phenomena. In Canada, the Sudbury Observatory uncovered neutrino oscillations, solving the long-standing mystery of missing solar neutrinos. Neutrinos change flavors, electron, muon, tau as they travel, a subtle quantum dance that had baffled scientists until recently. In 2002, Davis's decades of determination earned a Nobel Prize, honoring discoveries that redefined physics and cosmic understanding. These tiny particles hold the key to understanding the universe's birth, star evolution, and forces shaping reality itself. Learning from neutrinos forces us to accept that the universe is richer and stranger than what our eyes reveal, inviting endless exploration. Neutrinos lead us back to the profound mystery: why is there something rather than nothing? A question echoing through science and philosophy alike. Fear tricks us by bending reality, making threats seem nearer and more urgent than they really are to keep us alive. Brain takes seconds to process visual data, meaning we always see moments slightly behind the present our reality, a lagging playback. What appears yellow, the sun's actual emission is strongest in green photons, but atmospheric effects hide this truth from our eyes. We live bathed in waves beyond sight, ultraviolet rays, and infrared warmth, painting a hidden electromagnetic tapestry all around us. Among these waves, neutrinos constantly stream through matter and life, unseen carriers of universal history and energy. Born minutes after the universe's birth, neutrinos have traveled unscathed, holding secrets lost to all other forms of light and matter. Neutrinos were once dismissed by leading scientists, proving their existence took decades of perseverance and cutting-edge experiments. Wolfgang Pauli dared to propose a particle so elusive it left no trace, protecting physics' sacred laws but risking his reputation. Fermi named the little neutron neutrino, recognizing its ghostly neutrality as central to nuclear mysteries. Fermi's beta decay theory unveiled weak interaction, thoroughly altering our grasp of nuclear physics. Though Fermi's theory caused ripples in scientific waters, it laid the foundations for future breakthroughs. MOS Alpha Beta Gamma paper mixed science and humor, humanizing complex physics with playful names and cosmic imagination. Stars lose heat stealthily through neutrinos flitting away, a cosmic heist hidden in the universe's energetic dance. A chance interaction between Rheonese and Cowan sparked the first neutrino detection experiment, illustrating serendipity in science breakthroughs. Built a formidable detector near a nuclear reactor to trap fleeting neutrinos, a massive undertaking against particle invisibility. Double light flashes in the detector were neutrino's telltale signal, making the invisible detectable and confirming decades-old predictions. Pauli celebrated the neutrino's discovery, ending a long wait and honoring a particle once thought beyond reach. Though initially ignored, Fermi's theory profoundly influenced physics, guiding generations towards deep cosmic truths. Our sun relentlessly sends neutrinos streaming through Earth and all life, connecting us to the stars in unseen ways. Ray Davis's massive underground detector awaited neutrino interactions, a pioneering instrument in a new cosmic quest. Amid billions of neutrinos, Davis hunted rare flashes in a sea of invisible particles, an epic quest for cosmic whispers. Bubbling helium transformed neutrino impacts into light, allowing the invisible to reveal its secrets in bursts of glow. Davis's puzzling shortfall of detected neutrinos threw energy models into question, igniting decades of scientific mystery and debate. Davis's unwavering dedication through decades of scrutiny solidified his findings and reshaped physics understanding. Shiba's determined leadership propelled neutrino research to new heights, overcoming obstacles and opening a new observational frontier. Its detectors used blue Cherenkov light to uncover traces of neutrinos, transforming the invisible into vivid streams of color beneath Earth. 1987 marked the arrival of neutrinos from an exploding star, beating light by hours and revealing hidden cosmic dramas. Ghostly journeys and shape-shifting nature push us to rethink reality, reminding us that the unseen holds keys to existence's greatest mysteries. What truths do you think are hiding unseen?